Lesson 21 demo. Today we review inverse functions. More specifically, we'll look at logarithmic functions as inverses of exponential functions. This review will help us discover derivative formulas for inverse functions, including log functions, next class. So mostly pre-calc review today. Okay, here's an old AP question. If f of x is equal to x over x plus 1, then the inverse function, f inverse, is given by, and then this is a multiple choice. Those are 5 options. So let's go ahead and calculate the inverse function. So remember the idea here to calculate an inverse is first you change the f of x into a y. So all I'm doing is rewriting this thing, but change f of x to y. And then the next step is to interchange all of the x's and y's. So every y becomes an x, and every x becomes a y. And then we solve this new equation for the new y. All right, so there's a couple of y's here. I don't like that they're part of the same fraction. Let's multiply both sides by y plus 1. This will get rid of the fraction. Now there's y's on both sides of the equation. So we're going to distribute the x first to unbury the 1y on the left. And then we're going to get all the y terms over to the right-hand side of the equation by subtracting xy from both sides. And now that all the y terms are on the right and no y terms are on the left, we're going to factor out the y on the right-hand side. And the nice thing about that moment right there is that it's the first time we had a single y in this equation instead of 2 of them. And that was the point of every algebra step that we did before, was to get all the y's on one side, no y's on the other side, so we could factor out all those y's and just compress them to a single y, which we can then solve for by dividing both sides by 1 minus x. And then finally, instead of calling it y here, let's give it a better name. This is really the function f inverse of x. So there's your process. In English, change f of x to y, interchange all of the x's and y's, solve the new equation for the new y, and then at the end, rename that y f inverse of x. So x over 1 minus x looks like choice C is our answer. Okay, number 2, do you know what these statements mean? I sure hope the answer is a resounding yes, but let's make sure. Y equals log base b of x. We just have to know sort of the pattern here. This equation is equivalent to b to the y equals x. And so for me, this is just like following the arrows around. You take the base, you raise it to whatever is over on the other side of the equal sign, and then you cross back over the equal sign and you make the whole thing equal to whatever is inside of the log. And so just make sure you can follow those red arrows and see that they indeed translate to b to the y equals x. So this y equals log x is exactly the same. It's just a special case of the more general log equation we've written there. If there is no base written, then that means you are looking at the common log and the implied base is 10. And so we're just going to follow the pattern just like we did before. So this equation translates to 10 to the y equals x. And then the same deal for the last one. When you see ln of x, the implied base is e. This is specifically the natural log, whereas in part B, it's called the common log. So the natural log, it's a base of e every time you see ln. And so we followed the arrows in the same pattern as before. So we write the corresponding exponential equation, e to the y equals x. Number 3, for log of 800, guess the value of the expression, use your calculator to find the value of the expression, and then write a valid exponential equation that relates 800 and the answer from your calculator. Okay, so what is log of 800? Well, let's give it a name. How about we call it y? And just by giving it a name, we have given ourselves the opportunity to translate this into an exponential equation. So remember, this is the common log. When no base is written there, it's implied to be a 10. So that equation is equivalent to 10 to the y equals 800. And now I have something I can wrap my brain around. So for example, if we let y equal 1, then 10 to the first is 10. And if we let y equal 2, then 10 to the second is 100. And if we let y equal 3, 10 to the third is 1,000. And 800 is our magic number. And 800 is someplace in between 100 and 1,000. Therefore, the power that we want, the value of y that's sitting up here, has to be someplace between 2 and 3. 800 is darn close to 1,000, so probably my answer for y is going to be something closer to 3 than 2. So maybe we can guess. I don't know. Y is roughly, so we said closer to 3 than 2. How about 2.8? Really don't know. But something between 2 and 3, closer to 3. And then we'll just practice on the calculator. Make sure you can find this button. So log of 800 is all we're doing here. Log of 800 is what we're typing. The log button is on the left-hand side on my calculator. Expecting a number between 2 and 3, closer to 3. Good, pretty darn close to 3. So from the calculator, 2.903. And can we relate this 2.903 to the number 800? What does it really mean? Well, that 2.903 is the value of y, right? We guessed 2.8, but really 2.903 is more accurate. And so that means it is the number that when I take 10 and raise it to that number, I should get 800. So that means that 10 to the 2.903 should be 800. Okay, but it's not going to be perfectly 800 because I rounded, right? I didn't use all of the digits. So I'm going to store this number as x real quick, but then I'm going to type in my rounded version here, 10 to the 2.903. That's not right. 2.903. And we should get something very close to 800, 799.8. If I really wanted to get exactly 800, I should have used the unrounded number. So if I do 10 to the x, right, that's the more accurate answer the calculator has stored, then it tells us exactly 800. Okay, what's the relationship between f of x equals e to the x and g of x equals ln of x? These functions are inverses of each other. Five, what's the relationship between graphs of two functions that are inverses of each other? So these graphs are symmetric over a particular line of symmetry. They are symmetric over the line y equals x, which is the 45-degree line going through the first and third quadrants. So let's see if we can use that fact on number 6, which says sketch e to the x and then sketch ln of x on these axes below. So for the first one, graphing e to the x, we're going to go ahead and make a quick table here, a very rough table. So for example, at -1, 0, 1, and 2. So if we do e to the -1, this is going to be super approximate here, but it's around a third. So we'll call it roughly 0.3. E to the 0, that's easy, that's 1. E to the 1 is about 2.7, and e to the 2 is, I don't know, 8 point something. Second e to the 2. Oh, 7 point something, 7.4 roughly. 7.4. And so I can plot those 4 points. So it's around here, and then here, and then 2.7, and then 7.4, right around there. And so then we can draw an orange here, graph of y equals e to the x. Horizontal asymptote is the x-axis, and then it grows very quickly. And now we're going to do the same thing to graph ln of x. So this time we'll do a green table here, x and ln of x. But I'm actually going to do this without touching the calculator. And the way that I'm going to do this is to just recognize that when you go from a function to its inverse, something very specific happens with inputs and outputs. When we did the solving for the inverse function in the first problem in today's demo, one of the early steps was to swap the x and y, and that's exactly what we're going to do here. The relationship between a function and its inverse involves swapping the coordinates, swapping the x and the y. So my first point in my blue table was -1, 0.3. This one is going to be 0.3, -1. 0, 2.71, and then 7.42. So we're going to plot those points. So 0.3, -1 here. Not quite there. 0.3, -1, maybe around there, and then 1, 0, 2.7, and then up 1, and then 7.4 and up 2. So we will draw in red the ln function. So it's got a vertical asymptote of the y-axis, just like the e to the x had a horizontal asymptote of the x-axis. These two graphs are perfectly symmetric about the line y equals x. And you can see that one reflects right over onto the other. Common misconception is that because the ln grows so slowly that it actually levels off, like it has some horizontal asymptote up here, but it does not. This curve right here forever goes to the right and up. Therefore, this curve over here forever goes up and to the right. Okay, so number 7 is just a review of some log properties. Log of a times b, if you have the log of a product, you can split that up into 2 logs with a plus sign. Likewise, if you have log of a quotient, you can do 2 logs with a minus sign. Make sure you put the one on top first before the minus sign. If you have log of something to a power, you can take that power and peel it right off and bring it to the front, p log of a. This property is money. Ln and e to the x are inverses, so they cancel each other in this order, and they also cancel each other in this order. Note there's no basic property for log of a plus b. Do not try to invent one. It's not going to work. So number 8 says we're now in position to be able to solve a new class of equations whenever the unknown is in the exponent used logs. So we have not solved any equations this semester where the unknown was in the exponent because we didn't have this tool, but now we've got the tool. So I see the variable is up here in the power. So log is the right tool, but it isn't the right time to use that tool. First, we need to get the exponential part by itself. We need to get this thing by itself before we do log of both sides. This is equivalent to in the last couple of classes where we've gotten the trig part by itself before we either went to a unit circle or used the inverse trig button on the calculator. So here we're going to divide both sides by 100 first. And now that the exponential piece is by itself, log is the right tool. I'm going to copy this, but give myself a little bit of space. We're going to take the log of both sides. Which log should we take? Any log you want. I'm going to use ln. ln is the most common thing that we're going to use in the calculus class. You'll see why. Next class, it's because the derivative of ln is nicer than the derivative of the log of any other base. But you are welcome to use the common log here or log base 17 if you wish. Any log is fine. Okay, and then the left-hand side we're just copying. But the right-hand side has a log of 1.01 to the 12t. Maybe I'll put extra parentheses here, there, and there. And this is one of our properties. When you have log of something to a power, we said that we could take that power and peel it off and bring it right in the front. And that's what we're going to do. So the 12t comes right off of the log, and all that's left inside the log is the 1.01. And that is why logs are useful. They allow you to take a variable that's in an exponent and get that variable down to like the regular level. And now this equation is easy to solve. We're going to divide both sides by 12 ln of 1.01. Divide by 12 times ln of 1.01 equals, and when I divide the right-hand side by 12 ln of 1.01, I just get t. So there's my answer. That's an exact answer. If you want a decimal approximation, of course, you can use the calculator. We'll do that because we haven't used the log button yet. So my calculator has 2 log buttons. It's got the common log and it's got the natural log. I chose natural log here. So ln of 2 divided by, make sure we get parentheses around the bottom, 12 ln of 1.01. And so look at our decimal there. I had said you could use any log you want. So for example, if we had used log, common log, on both sides, then both of these ln's would be common log. So the answer would look different here. But when we type it in, we're going to get exactly the same decimal. Divided by parentheses 12 log 1.01. Okay, so we'll just say this is roughly 5.8 here. So 5.8 is our approximation.